Yeah, now let's look up for a few numerical problems on the discrete distributions. We have discussed the binomial, then Poisson, then geometric, hypergeometric, right? So using all these negative binomial, using all these distribution, how do I typically solve some of the questions? Though most of the questions which we come across in the exam would either fall into the category of Poisson distribution or binomial distribution. But yeah, it's better to know a couple of other kinds of distributions and the numericals on them also. So going ahead with the first one, claims on a group of policies arise randomly at an average rate of 2 per month. So whenever there is a number per a time period, we can always use a Poisson distribution. Calculate the probability that no claims arise in a particular month. So the information that is given to us is lambda equal to 2. So we are supposed to find out probability of x equal to 0, which is nothing but e power minus lambda into lambda power x divided by x factor, which is nothing but e power minus 2. So we can say that this is the probability that no claim arises in a particular month. Now he is also saying calculate the probability that more than 30 claims arise in a 1 year. More than 30 in 1 year is as good as, probably you can very well take it as more than 2.5 claims per month. So again you can go with the same logic, or probably you can here say 24 claims. 24 is the lambda. So either the thing, you can convert this to this or this to this. So you can talk about probability of getting more than 2.5 claims in a year, which means you can find out probability of either getting 0 claims in a year or 1 or 2, and subtract it from 1, which will give you more than 30 claims in 1 year or 2.5 claims in a month. See the more than 2.5, right? So more than 2.5 means see 3, 4, 5, 6, any could be there. So all I am saying is, other than that, you find out 0 claims, 1 claim and 2 claims, which is like find out less than 2.5, because it is a discrete. Only 3 of these things are possible. You can very well work out for Poisson is a discrete distribution itself, right? You can find out these 3 and you can do a 1 minus of that. Okay, now let's look at the next one. Okay, so just like one of the numerical we have done on continuous, calculate probability of x less than 8. X is the number of claims reported in a year by 20 policy holders. Each policy holder makes a claim at the rate of 0.2 per year independently of other policy holders. So we are talking about 20 policy holders. So the lambda for those 20 policy holders is 20 into 0.2, which is 4. So the lambda for 20 policy holders is 4. Now the question is asking of what is the probability that the number of claims is less than 8. Less than 8 is nothing but it could be 0, 1, 2, 3, 4, 5, 6, 7. And we can use Poisson distribution here. Right? Poisson distribution here. So it is as good as saying, so my lambda is 4. right? So I need zero claim, zero claim, one claim, two claims. I need, because he is asking about probability of x less than 8, I need it up to 7. So e power minus lambda, lambda is 4, into lambda power x divided by x factorial, divided by x factorial, e power minus lambda into lambda power x divided by x factorial. So for 0 this is the case. So these are the cases for 0 to 7. So which is telling me 0.948 almost. So there is a 95% chance that the number of claims will be less than 8. There is a 95% probability that the number of claims will be less than 8 in this particular scenario. So I can use Poisson distribution for this kind of a numerical. Then X is the number of claims examined up to and including the fourth claim that exceeds 20,000. So number of events up to the nth success, up to the kth success. That is what we have to model here. I want fourth claim that exceeds 20,000, which means I am looking out for the number of success. So probably I am looking at different claims. I am stopping where I am coming across a fourth claim which has crossed 20,000. Now he is asking me the probability that any claim received exceeds 20,000 is 0.3. So the thing which I can very well use in this case is a negative binomial distribution. Number of trials up to the kth success. Number of trials up to the kth success is what is our negative binomial distribution. If we go back to see our negative binomial, this one, used to model the number of trials for the kth success. Here also when I am saying kth success, fourth 20,000 plus policy. So I have to go with this kind of a formula, x minus 1 ck minus 1 into p power k into 1 minus p to the power x minus k. Okay, so applying the same. So here we are saying the probability is 0.3. Okay, so the probability of success is 0.3, which means probability of failure is 0.7. We are talking about that x should be less than 8. But I need the fourth success. So probably I can have, in 4 itself I can get 4 successes. In 5 I can get 4 successes. In 6 I can get 4 successes. In 7 I can get 4 successes. Because I want up to the fourth success. So within 4 trials itself, the first 4 policies which I am observing itself could be 20,000 plus policies. Or by the time I look at the 5th policy, it could be 20,000, 6th or 7th. All, I mean see, one possibility is just observe the first 4, all 4 are 20,000 policies. Right? If that is the case, what is the probability that the first 4 itself are, 20,000 plus policies? Right? I am observing the 4. What is the chance that 4 of them are 20,000 plus policies? So that is where I am looking at 4C4. So 4C4 into p power 4 . 4C4 4C4 into P power 4 into 1 minus P to the power x minus 4. So this is coming out as there is only 0.8% chance that all the first 4 policies are 20,000 plus policies. Then next it is saying that there is a slight chance that out of the 5 policies, point 3 power point sorry 0.3 per 4 so yeah, now it is saying there is a 0.08% chance that the first 4 policies itself are 20,000 plus policies. Now for if I am saying okay, the possibility could be within 5 policies there could be 4. The fifth policy could be a 20,000 plus policy. So my fourth success could occur there, or my fourth success could occur with the sixth policy, or my fourth success could occur with the seventh policy. My fourth success occurring with seventh policy means what? 3 policies are failures. In the 7 policies, 3 are definitely a failure and 4 of them are success. That is what it is. With the 7th policy, if I am talking about my 4th success, then that is how it works out. So the simple formula which I am applying there is nothing but this. You can just rely on this formula. This one, which is saying if you are looking at let's say the 7th policy. For the 7th policy, what it is saying, x minus 1, 6C3 oh, we have taken xck. X minus 1 x minus 1 ck minus 1. So x minus 1 ck minus 1 p power k 1 minus p, this part is correct, p power k 1 minus p power x minus k. Okay, so I think there's a small change then. Yeah, these are the probabilities. So all we are saying here is if I want seventh trial to contain 4th success, which means within the 6 trials I should have 3 successes. So 6 trials, 3 successes means 3 failures, and the 7th trial is a success. So that's where we are applying the formula 6C3 into 0.3 per 4 because 3 successes and the 7th one is a success. So 0.3 to the power 4 and to the 0.7 to the power n minus k, 3 failures. Right. So if I add up all these things, it is telling me that up to the or less than 8 trials, the probability that you will find the 4th claim of 20,000 plus within less than 8 trials is nothing but around 12.6%. That is how you use your negative binomial kind of a distribution, especially to find out the questions relating to the kth success. Then you have X is the number of deaths among a group of 500 policyholders. Each policyholder has a 0.01 probability of dying independently of any other policyholder. You can use binomial distribution because I want less than 8 deaths. So, out of 500, 0 people die. Out of 500, 1 people die. Because there are only 2 outcomes, death or non-death. Right? So, we can use binomial, or as we have also discussed, if n is very large and the probability of success is very, very small, the NP can be taken as a Poisson approximation also. So, you can very well take NP equal to lambda, which is 5. And you can go ahead with the lambda Poisson distribution also. Or you can depend on binomial. There will be small difference, but you can very well consider both of them. Especially when your number of experiments is very large and the probability of success is very, very small, you can very well do the multiplication of n and p and take lambda as a constant and use a Poisson distribution. Otherwise, you are going with a binomial distribution, saying 500 C 0.01 to the power 0 into 0.99 to the power 8. This is P of x equal to, 0.99 to the power 500. This is P of x equal to 0. 0 deaths. 1 death, same way. 500 C 1, 0.01, 0.99 to the power 499. Similarly, you can do up to 7. And you can add up and say this is the probability that the number of deaths is less than 8 out of the 500 people. Sorry? C8. Less than 8 is what we need, right? Up to 500 C500 means it is 1 again, the total probability. We need it only up to less than 8. So, up to 7 you may have to do. So, if it is becoming very tougher, probably you can make this approximation of NP equal to lambda and you can directly apply a Poisson distribution. Even that Poisson distribution you have to do up to 8 probability of, but probably Poisson distribution is easier to compute compared to a binomial distribution. Right? Then, X is the number of phone calls made before an agent makes a first sale. First sale. So, it's a geometric distribution. First success. Number of failures before a first failure. First success. It's not number of events up to the number of trials up to the first success. It is talking about number of failures before the first success. Right? So, if I am talking about, okay, the probability that any phone call leads to a sale is 0.01 independently of any other call. So, probably you can talk about X less than 8 means you can talk about, see, if the first sale is happening in the first trial itself, then there are like 0 failures, 0 phone calls. Or there could be 1 phone call before the first success. Because he is saying X is the number of phone calls. So, I can make 0 phone calls before the first sale. 1, 2, 3, 4, 5, 6, 7. And what is the distribution I have to use? Geometric, which is the second part of the geometric. The type 2 geometric distribution, which is number of failures before the first success. Number of phone calls before the first sale. So, we are talking about P into 1 minus P to the power X. So, when I am talking about 0 phone calls, P into 1 minus P, so 0.01 into 0.99 to the power 0. This is 0 phone calls. Right? So one phone call. So probably it is coming out like, so I can make 0 calls, 1 call, up to 7 calls can be made, because he is asking about x being less than 8. So 0.01 into 0.99 to the power x. So it is saying some around 0.07 or 7.7% chance is there that you will make less than 7 calls, because the probability of success is only 0.01. So within 7 calls making a success is a very small chance, because probably this is itself saying there is only 1% chance of converting a call into a sale. So only 7 calls creating the first sale, the chance is very much slimmer. And that is what even this value is saying. There is only 7.7% chance that you can convert it into a sale. Right? So like this, you should be able to identify the appropriate distribution. And as I said, once you know the distribution, the formulas and all are available for us. All I need to know is what is an appropriate distribution in this scenario. If I am talking about the kth success, yes, I have to think of negative binomial distribution. If I am talking about the first success, probably I have to look at the geometric, which is a special case of negative binomial. And if we are talking about out of n independent events, n success, k successes coming out, not events up to k success. We are talking of k successes, like the third question. Number of deaths out of 500. Then we are using a binomial distribution. So if we understand the context of the distribution, formulas and everything are available in the tables, we don't need to bother about them. So here the intention is not to mug up the formulas. Alright. Now, derive an iterative formula for the probability function of a Poisson distribution. These are sometimes they are using these kind of questions. Iterative is nothing but, probably if you find out both of them, probability of x equal to x, and also find out probability of x equal to x minus 1. Express one in terms of the other. That is what is an iterative formula. So if we are just seeing this, for any distribution, he may ask you for an iterative formula. So when I am saying probability of x equal to x, we are saying e power minus lambda, lambda power x by x factorial. Okay, p of x equal to x minus 1, e power minus lambda, lambda power x minus 1 divided by x minus 1 factorial. Now you try dividing one by the other. P of x equal to x by p of x equal to x minus 1 is equal to, here e power lambda is getting cut off. So you are left with lambda by x. Lambda by x. So it's as good as saying p of x equal to x. So this actually helps you. You just do a lambda by x into p of x equal to x minus 1. So let's say in some of our previous numericals, x less than 8, he has asked. Right? The moment I find out for x equal to 1, right, I can find probability of x equal to 2 directly from here. Lambda by x, which means lambda by 2, into whatever the probability that came with x equal to 1. So even here if you see this question, this was the probability distribution itself. So for if I want for 1, all I can do is lambda by x. In this case lambda by x, this is x. lambda by x into the previous probability. So what could happen is work will get simplified for us. Lambda by x into previous probability. We get the same numbers. But without doing, for every time I don't need to do e power minus lambda, that multiplication I don't need to do every time. The moment I get my previous answer, that answer I will do just a multiplication by lambda by x. So like that, for every formula, for every distribution, he may ask us to find out an iterative formula, which is nothing but you will do this kind of an exercise, right? So you will find for x, you will find for x minus 1, try to express x in terms of x minus 1. All right. Then, yeah, a random variable x has a Poisson distribution with 3.6 lambda. What is the mean of the distribution? Mean, variance, both of them are 3.6. I don't need to find them out. So mean is 3.6. Variance is 3.6. So standard deviation is square root of 3.6. Both are same. In Poisson is one of the only one distribution where you are finding both the mean as well as variance, not standard deviation. Mean and variance are same. So you can directly take the variance, square root of the variance, square root of 3.6 is your standard deviation. Now, this is a slightly interesting question. How do I find out the median? How do I find out the median in case of Poisson distribution? Simple thing what people say is whether it is median or mode. The simple exercise is you start doing from 0, 1, 2, all, as many as possible. Where your total cumulative touches more than 0.5, 50%, that is your median. So here you are doing e power minus lambda into lambda power x by x factorial. So this is the probability for x equal to 0. The same way I can continue. Do the cumulative now. Where whichever class contains 50%, the first class, that is the definition of median. Whichever class contains whichever the value contains the 50%, this one, you say the median is 3. You can say that the median is 3 in this case, right? That's the same. You don't have any other method to find out the median. Wherever the cumulative, even in case of in continuous, what did we do? We did the integration and equated that integration to half. Wherever you have to find out the median in case of continuous distribution, we do an integration of the probability function and then equate that integration value equal to half. That is where we will find out the median. Here we are doing a summation and seeing where the summation is equal to half. And that is what is our median value. So I can directly say that the median is 3 in this case. And how do I find out the mode? Whichever the one that comes maximum frequency. You are seeing that up to here it has gone up and after that it is falling down. So again the mode is also 3. This is probably, these are some tricky things he will ask. Finding out mean and standard deviations are always straightforward. Formulas will be available. So finding out these kind of things will be slightly tricky for us. So when you are talking about it, finding out the median and the mode. Median, all you will do is you will take the cumulative and find out where it has crossed 50%. Mode means you will just see the frequencies which has occurred the maximum number of times. And comment on the skewness of the distribution. How do we comment on the skewness? Simple way to comment. You don't need to compute the skewness. If mean is greater than the median, if we see mean is greater than the median, we'll say it is positively skewed. And mean is less than the median, we can say it's a negatively skewed. So in this case, mean is 3.6 and median is 3. So we are directly saying that it could be a positively skewed distribution. You don't need to calculate the skewness and all these things of the distribution. Right? You can very well say that it is a negatively, it's a positively skewed kind of a distribution. So it is symmetric. Okay. The random variable n has a Poisson distribution with parameter lambda. P of n equal to 1 given n greater than or equal to 1 is 0.4. So how do I find out probability of n equal to 1? See, n equal to 1 given n greater than or equal to 1 is nothing but probability of 1 and greater than or equal to 1, which is numerator is still probability of 1 only. So it's as good as probability of 1 divided by probability of n greater than or equal to 1. Right? Now what is the probability of 1? E power minus lambda into lambda power 1 by 1 factorial. That is the probability of 1. Now what is the probability of n greater than or equal to 1? I can just find the probability of 0 and subtract that value from 1. Then it is greater than or equal to 1 only. It could be 2, 3, 4, 5, 10, 100, 200. It's just not 0. Rest all it could be. Right? So what is the probability of 0? E power minus lambda, lambda power 0 by 0 factorial. So e power minus lambda is the probability of 0. But I need rest all. So 1 minus e power minus lambda. So my expression actually is becoming lambda e power minus lambda divided by 1 minus e power minus lambda equal to 0.4. Fine. So probably if you want, you can simplify it. Lambda e power minus lambda is equal to 0.4 minus 0.4 e power minus lambda. So you take it other side, e power minus lambda into lambda plus 4, lambda plus 0.4 equal to 0.4. If there is some way, or you can go with a trial and error kind of a mechanism itself here. If you want to solve this kind of an expression, or what you can do is, okay, e power minus lambda into lambda plus 0.4 equal to 0.4. Trial and error mechanism itself is a much better suited because there is no other direct way to solve this. No, I think you should resort to just substituting some value for lambda and checking out itself. So let's see. Lambda e power, so if I'm just taking lambda equal to 1, 2, 3, just quickly checking out. So this is nothing but lambda e power minus lambda divided by 1 minus e power minus lambda. Okay, so this is 0.58, but I still need 0.4 only. So probably you can just do the next 2 exercises. So we are now here that it should lie between 1 and 2 only. Because for lambda equal to 1, we are getting the probability is 0.58. But for lambda equal to 2, we are getting it as 0.31. So we know that it should lie between 1 and 2. So probably if I am quickly trying out 1.5, yeah, 0.43, coming closer to it. So probably 1.6, yeah, almost 0.40. So probably you can say 1.6 is the value of lambda. So in this case, there is nothing but trial and error, but the simple way to operate is probably just take two values and try to extrapolate or interpolate from those two values. From an exam standpoint, you can just compute for two values, take some lambda equal to something, lambda equal to something else. Based on those two values, try quickly doing your interpolation or extrapolations. Fine. Using the all these will be available with the scientific calculator. E powers. No, as I said, you do it only with one or two values. You say lambda equal to 1, lambda equal to 2. Only two calculations you will do. Now you will see whether that 0.4 is within this interval or below these two values or above these two values. If it is within the interval, you will just do 1.5, 1.6 kind of stuff. If it is below, then you will do 0.5, 0.6 or 0, couple of more checking. But yes, I mean that kind of simplification, even if you just leave it there also, probably 1 or 2 marks could be impacted, but not more than that. So if a quick number can work out for you, see, and that too if you are seeing n equal to 1, given n greater than or equal to 1 is 0.4. So n equal to 1 is very solid. So at least I can make out that the number should be somewhere in that surroundings itself. Right? Because there is no direct way to solve these kind of, and otherwise you have couple of other methods basically to solve any kind of an expression. The other day I have given you the Newton-Raphson kind of a method to solve any equation. Even that kind of a method can help you to solve it, provided you are able to simply, even you can use that method also to solve this equation. The way that method goes is, you start with 1. Let's say lambda equal to 1. You start with some number. Let's say you got 0.58. What it says is, if you are able to find out the differentiation of that expression, e power that lambda, probably you just go through the Newton-Raphson method one. See what but that is also a complex process in this example. What it says is you should be able to differentiate this function. You have to find out the derivative of that function and then substitute the values into that function, and it keeps reducing or increasing, which will take you closer to the solution. Right? Okay, if the random variable x has a Poisson distribution with mean lambda, derive an expression for expected value of 1 by x plus 1. So any expected value calculation we have seen earlier, you just multiply it with the probability function. Right? Expected value of 2x plus 1 or 3x squared, if whatever we had to do for variance calculation when we had to do expected value of x squared, we did that nothing but that function multiplied by the probability function, e power minus lambda, lambda power x by x factorial. And this is the complete summation. I have to add up all of them. See, you multiply it with the probability and you add up. That is what is the expected value when you are given a table kind of stuff. You multiply each number by its corresponding probability and then add up. Right? So here also we are doing the same, which means what is coming out to me is integral this, if I see e power minus lambda power x, the denominator will become x plus 1 factorial. So probably what I can also do is I'll do 1 by lambda here and multiply denominator, I'll multiply and divide by lambda, so that this also becomes x plus 1. So I'll do sigma e power minus lambda power x plus 1 by x plus 1 factorial. I have just multiplied and divided by lambda so that I can express it in this form. Right? Here the trick is there. Okay. This is from 0 to x equal to from 0 to infinity. X is from 0 to infinity. But if you see here, it is starting from 1. So it is actually missing out on 0. If you are saying x is from, in this case, if you are saying x equal to 0 to infinity, here we are getting the value right from 1. We are not getting the 0 part. Or better, let me put it slightly different for you. This I can take out e power minus lambda by lambda out, and I can say x equal to 0 to infinity lambda power x plus 1 by x plus 1 factorial. Fine. Now what is it coming out like? Lambda by 1 plus lambda squared by 2 factorial plus lambda cube by 3 factorial. This is what is the expansion, right? Actually, the expansion of e power lambda, this is some mathematical expansion which you must be comfortable with. The expansion of e power lambda is nothing but 1 plus lambda square by 2 factorial plus 1. So what you are seeing here is 1 is not there in this. Rest all is there in e power lambda expansion. So probably I can write this as 1 minus e power lambda minus 1. The e power lambda expansion is 1 plus lambda squared by, this is a mathematical expansion. E power x. When I say e power x, it is nothing but 1 plus x squared by 2 factorial plus x cube by 3 factorial plus so on. But I want just x plus, because this is the expression. I require x plus x squared by 2 factorial plus so on, which is nothing but it is e power lambda minus 1. So in a way it is becoming e power minus lambda by lambda into e power lambda minus 1. In other way, this is becoming 1 minus e power minus lambda by lambda. This is the, so one couple of things which you have to remember in this case is, whenever you are having this form, lambda per n by n factorial kind of summation, you can very well look at e power lambda expansion. Right?